Picture a scientist on a grey winter morning, sitting at one of the first computers big enough to fill a room, running a little toy version of the weather. He wants to look at one stretch of the forecast again, so instead of starting over from the beginning, he types in the numbers from a printout partway through and lets it run. Then he walks down the hall for a cup of coffee. When he comes back, the weather the machine has drawn is nothing like the run before. Not a little off, completely different. A calm sky where there'd been a storm. Same equations, same machine. The only thing that changed was that he'd copied one number a hair less precisely than the computer had been carrying it. A difference so small it seemed like nothing at all, in a world made of nothing but rigid, exact rules. And it rewrote the future.
I love that you started there, because that moment actually happened, and it's one of the true turning points in 20th century physics. The man was Edward Lorenz, a meteorologist at MIT, and the year was 1961. He wasn't trying to discover anything, he was just restarting a run to save himself some typing. The printout rounded his numbers to 3 decimal places, but inside, the computer had been carrying 6. So he typed something like 506, when the stored value was really 506127, throwing away a sliver past the 3rd decimal, about 1 part in 1,000. He fully expected it to make no difference at all.
And instead, the two forecasts peeled apart.
Slowly at first. For a simulated day or so, you could barely tell them apart. Then the gap doubled and doubled again, and within what would have been a couple of simulated months, the two runs had no resemblance to each other at all. And Lorenz sat there and realized he was looking at something genuinely unsettling. A system that obeys perfectly definite laws, with no dice and no randomness anywhere in it, that is nonetheless impossible to predict for very long. That single accidental keystroke is, more or less, the birth of what we now call chaos theory. But Newton said, the future is fixed.
This collides head-on with the very first thing I ever learned. Newton's laws are deterministic. That's the whole deal. If you give me the positions and the velocities of everything right now, and you give me the forces, then the future is completely fixed. I just turn the crank and the equations spit out where everything is a second from now, a year from now, forever. There's no room for surprise in there. So how can a system that runs on those laws be unpredictable? That sounds like a flat contradiction.
It sounds like one, and it kept very smart people from taking this seriously for decades. And you are completely right about the physics. Determinism is true. The laws really do fix the future uniquely, and I'm not going to take that away from you. What I'm going to do instead is drive a wedge between two words you've quietly been treating as one.
Determined and predictable.
Determined and predictable. Prying those two apart is the whole heart of tonight. But first, I want to plant this in something you've actually solved on paper. In your mechanics course, you did the pendulum. The simple pendulum, a weight on a rod, swinging.
Sure, small swings. It's just the harmonic oscillator, clean sine wave, fixed period, the thing you can set a clock by. It's the best behaved system there is. Push it a little differently and it does almost exactly the same thing, just shifted a hair.
Exactly. And that, push it a little and it does almost the same thing, is a property you've unconsciously assumed is just how the world works. Now let me make one tiny change to the apparatus. Take that pendulum and at the bottom of the rod, attach a second rod with a second weight on a free hinge. A pendulum hanging off the end of a pendulum. A double pendulum. One extra joint. You could build it out of 2 rulers and a couple of bolts in an afternoon.
And I'm guessing it does not give you a nice clean sine wave.
It goes berserk. It flips, it whirls, it kicks, it stalls and drops. It dances a completely different dance every single time. And here's the part that should bother you. If you build 2 of them as identically as human hands can manage, and release them from as close to the same angle as you physically can, They'll track each other for a second or two, and then they diverge and go do totally unrelated things. Same rods, same length, same laws. Newton's laws, the ones you just defended. And yet the motion is wild and past a couple of seconds, unrepeatable.
Wait though, let me flag this before you run away with it. Isn't that just because it's messy? Real bolts have friction, the air pushes on it. My hand is shaky when I let go. That's not the laws being unpredictable, that's just me being sloppy in the lab.
That is the single most important objection in the whole subject, and the honest answer is the surprising one. It is not about sloppiness. Take the double pendulum out of the messy lab entirely. Put it in the mathematics, where there's no air, no friction, no wobble. A perfect, idealized double pendulum, obeying Newton's laws exactly. It is still chaotic. Two flawless copies, started a hair apart, still peel away and do unrelated things. So let's retire "it's just noise" right now. The whole shock of this field is that the unpredictability survives even after you scrub out every last bit of noise. It's not in the mess, it's in the laws themselves.
So, the double pendulum is the simple pendulum's unhinged cousin, one extra joint away from the thing I can set a clock by.
One hinge past the pendulum you solved for homework, and that one hinge is the doorway. Everything we talk about tonight is on the other side of it. Deterministic is not the same as predictable. So let's pry those two words apart properly, because it's the one idea I want you to walk out with. Newton says, "Give me the exact present, and I'll give you the exact future." That is true, but look hard at the hidden word in there. Exact. We never ever have the exact present.
Right. Any measurement I make has some uncertainty. I know the angle to within a little bit, the velocity to within a little bit. There's always a last decimal place I don't actually know.
Always. So the real question, the one that decides whether you can predict a system, is this. You start out not knowing the present perfectly. There's a little smudge of uncertainty around your starting point. As the system runs forward, does that smudge stay small, or does it grow? That's the whole fork in the road.
And for the systems in my textbook, the smudge stays small.
For most of them, beautifully small. If you're a little bit off about where a planet is today, you're a little bit off about where it is next week. The error just comes along for the ride, roughly the same size the whole way. Small mistake in, small mistake out. But a chaotic system does something else entirely. The smudge does not stay the same size, it grows, and not just grows, it grows exponentially. It doubles. Then the doubled version doubles. Then that doubles again.
And exponential growth is the sneaky one because it looks slow and then suddenly it's everything.
That's the entire trick. Say your uncertainty doubles every so often. A hair's width of doubt, doubled enough times, becomes the whole width of every possible weather there could be. So at the start, your prediction is superb. A little later, good. A little later, useless. Not because the laws got fuzzy, but because your tiny, unavoidable ignorance about the starting point got amplified until it swamps everything. Here's the one sentence I want you to keep. In a chaotic system, the error doesn't add up. It multiplies up.
And that's Lorenz's keystroke exactly. His mistake lived a few places past the decimal point. Digits so far down they looked like nothing. And the machine just kept multiplying it until 2 simulated months later, it filled the entire forecast.
That's precisely what he'd stumbled into. And there's a formal name for it, sensitive dependence on initial conditions, which is a mouthful, so it got a nickname. In 1972, Lorenz gave a talk with a title that's now famous. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? And that is where the butterfly effect comes from.
Which I have absolutely heard mangled into mysticism. Everything is connected. A butterfly sneezes and the whole world shifts. It's all cosmic and fated. That's not what he meant, is it?
Thank you for catching it. Because no, and the real meaning is sharper and better than the mystical one. It's a deliberately vivid picture, so let me label what it is and isn't. It does not mean that one specific butterfly reaches out and causes one specific tornado. You could never trace a line from that insect to that storm. What it means is that the final outcome depends on the starting detail so finely, down past any decimal place you could ever hope to measure, that a difference as tiny as a wing flap is enough to eventually land you in a completely different weather. The cause isn't magic, it's exponential sensitivity to details too small to ever pin down. Lorenz meant it precisely, and precise is more astonishing than the fairy tale.
Okay, and let me nail one more thing to the wall while we're here, because my brain keeps trying to file unpredictable under random. Is this randomness? Is there some cosmic dice roll sneaking into the double pendulum?
No. And this is the misconception I would most like to kill tonight. So let me say it as flatly as I can. There is no randomness in here at all. The rule is rigid. The double pendulum, the little map we're about to meet, Lorenz's weather model. No dice in any of them. If you could feed in the truly exact starting numbers, every digit, infinitely many of them, the future would be fixed and reproducible down to the last detail. It is not a dice roll, it's more like an infinitely detailed clockwork, perfectly determined gears that happens to be built so that the tiniest nudge sends it somewhere wildly different. Unpredictable because it's sensitive, not because it's random.
And I have to ask the question every physics student asks right here. Isn't there already unpredictability baked into the universe from quantum mechanics? Is this the same thing wearing a different coat?
Different animal entirely. And I'll give you one honest sentence and then park it, because it's a whole other evening. Quantum indeterminacy is a genuine, built-in fuzziness in the laws themselves. The universe apparently doesn't hold a definite answer until you look. What we're doing tonight is completely classical. The laws are perfectly definite and certain, and the only fuzziness is in our knowledge of the starting point. Two totally different sources of unpredictability. Tonight is strictly the classical one. The quantum one we leave for another day. One line of arithmetic.
You keep promising me something with chaos in it and no randomness, and I want to see it because right now it's all pendulums and metaphors. Show me the simplest possible version.
Let's do it. And it really is almost insultingly simple. One line of arithmetic you could run on the calculator in your pocket. Imagine you're tracking a population, rabbits in a field, say, but written as a fraction of the most the field could ever hold. So it's a number between 0, meaning extinct, and 1, meaning absolutely packed. To get next year's number from this year's, you do exactly one calculation. Take a knob we'll call R, multiply it by this year's fraction, and then multiply that by 1 minus this year's fraction. That's the entire model. That last piece, the 1 minus part, is just crowding. When the field gets too full, they breed less.
So there's one knob, R, and I turn it, and each year I feed last year's number back into the same little formula. That's it. That's the whole universe of this thing.
That's the whole universe. And it has a name, the logistic map, and a hero who made it famous. A biologist named Robert May in a paper in the journal Nature in 1976, whose entire point was that a simple deterministic rule can behave in ways that look outrageously complicated. So let's turn the knob. Start with R small. What happens is boring in the best possible way. The population just settles down onto one steady value and sits there, year after year after year. Calm, predictable.
Fine, turn it up.
Turn it up past a certain point. It happens right around R equals 3, and something new is born. The population stops settling on one value. Instead, it starts alternating between two. A high year, a low year. High, low, forever. It has split in two.
A 2-year cycle. Still totally predictable, though. I could forecast that in my sleep.
You could. So keep turning. Push R a little higher, and each of those two values splits again. Now it's a 4-year cycle. 4 values, then repeat. Higher still, and 4 becomes 8. Then 8 becomes 16. Each nudge of the knob doubles the length of the pattern, and, crucially, the doublings come faster and faster, crowding together as you go.
This is that word, period doubling. The period, the length of the cycle, keeps doubling. 2, 4, 8, 16.
Period doubling. And it's a cascade because those thresholds pile up closer and closer until they slam into a wall. A particular setting of the knob, right around 3.57, where the cycle length has, in effect, doubled infinitely many times over. And past that wall?
Let me guess, it never repeats.
It never repeats. Past that point, the population hops around forever without ever settling into any cycle at all. One multiplication done over and over with no randomness anywhere, and the output looks, to any test you throw at it, effectively random. Deterministic chaos in one line of arithmetic. And there's a lovely twist. Even out in the chaotic zone, there are narrow windows where order suddenly returns. A clean 3-year cycle appears from nowhere, then doubles its own way back into chaos.
That's wild. The simplest formula I've ever seen already contains the whole story. Settle, split, split again, off the cliff into chaos. But hang on, you slid a number past me. You said the doublings crowd together at a definite rate. Is there a number for how fast?
There is. And that number is the most astonishing thing in the whole field. It deserves its own moment. The number that shouldn't be everywhere. In the mid-1970s, a physicist named Mitchell Feigenbaum sat down, famously with nothing but a pocket calculator, and measured how quickly those period doubling thresholds bunch up. You take the gap between one doubling and the next, and divide it by the gap between the next pair, and you ask what that ratio settles onto as you go deeper and deeper into the cascade.
And it settles on some number.
It settles on a number, about 4.67, 4.669, and then on and on. And I want to be careful here, because it is not exactly 4.67. It's almost certainly a never-ending, never-repeating decimal. But here's the honest catch. Nobody has even managed to prove it's irrational. It's believed, not settled. So when I say 4.67, I'm rounding a thing we think has no tidy value at all. Fine, a number. Feigenbaum found it around 1975.
A number, so what? It's the doubling rate for one rabbit formula.
Ah, but it isn't just the rabbit formula. That's the whole thunderclap. Feigenbaum tried it with a completely different equation, just some other smooth curve with a single hump in it, and he got the same number, 4.67 again. He tried others, same number every time. It turns out that essentially any system that tumbles into chaos by this doubling route, any smooth process with a single hump to it, crowds its doublings together at that exact same rate. The rate does not care what the system is made of.
Hold on, the rabbits and some totally unrelated equation share the same number, to as many decimals as anyone cares to check.
I'm telling you more than that, because this isn't only about equations on paper. Go into a lab and set a faucet dripping, then slowly turn it up. The dripping period doubles on its way to a chaotic patter, and the rate is that number. Take certain electronic circuits and drive them toward chaos, that number. Heat a fluid until it starts to churn, that number again. A dripping tap, a circuit, a swirling fluid. No shared parts, no shared physics, nothing whatsoever in common except the way they fall into chaos, where they all carry the identical fingerprint. About 4.67. Physicists call it universality, and it is a proved, rigorous fact. Feigenbaum found it around 1975. The universality was worked out a few years later, independently also by a pair named Coulet and Tresser, and it was put on fully rigorous footing by Oscar Lanford in 1982. This is not hand-waving, it is a theorem.
That genuinely gives me chills, and I think I see why. The details don't matter. Whatever the system is, water, electrons, rabbits, the road into chaos has the same shape for all of them, and that shape has a number, and it's always this number.
You said it better than I did. Chaos, the very thing that makes systems look hopelessly individual, turns out to have a universal fingerprint hidden underneath it. There is deep, shared order in the way things become disorderly. And for a lot of us, that number is the exact moment this whole subject stops being a curiosity and turns into physics. A shape the flow is poured into.
So I've got chaos in a single number now, one line of arithmetic, one knob, but the double pendulum lives in space. It moves. It has position and momentum. What does chaos look like when it's a thing flying around and not just a number bouncing?
This is where we come back to Lorenz and to the picture that put a face on the entire field. Remember, his weather model wasn't really the whole atmosphere. It was 3 linked equations he'd stripped all the way down to describe convection, the way a fluid rolls over when you heat it from below. Warm fluid rises, cool fluid sinks, the whole thing turns over in rolls. He published those 3 equations in 1963 in a paper with a title that quietly announced the field's entire future: Deterministic Non-Periodic Flow. Deterministic, no randomness. Non-periodic, never repeats. Both at once. That paper is the founding document of chaos theory.
Deterministic and non-periodic. That's the whole tension, isn't it? Rigidly ruled and yet never doing the same thing twice.
That's the entire episode in a 2-word title. Now here's the picture. Take the 3 quantities in his model as 3 coordinates, so the state of his little weather at any instant is a single point floating in a 3-dimensional space. As time runs, that point traces out a path, a trajectory, curling through the space. And when you actually draw the path Lorenz's equations trace, you get one of the most beautiful objects in all of science. 2 great looping spirals side by side, like the 2 wings of a butterfly. The trajectory loops around one wing a few times, then flips over and loops around the other, then back, never in a repeating pattern, never the same number of loops, but always staying on those 2 wings.
So it's not formless. The chaos isn't just spraying everywhere. The path is trapped on this butterfly shape.
That is the deepest thing about it, and I want you to hold both halves at once. Globally, it is ordered. Every trajectory gets drawn onto this same elegant bounded shape and never wanders off it. It's called a strange attractor because it attracts nearby paths onto itself. But locally, in the details, it is utterly unpredictable. Which wing it's on next, how many loops before it flips, that part is pure chaos. 2 paths that start a hair apart end up on opposite wings. Ordered globally, unpredictable in the detail. That's the signature of chaos, turned into a shape you can look at.
Slow down on one word, though. I can feel a wrong picture sneaking in. When you say the point moves through a 3-dimensional space and traces a shape, that's not real physical space, is it? The butterfly isn't hanging somewhere up in the sky.
Beautifully caught. And no, and this is exactly the kind of thing that has to be labelled, or it quietly turns into a lie. The 3 axes aren't up, down, and across in a room. They're the 3 variables of the model. Roughly, how fast the fluid's rolling and a couple of things about how the heat is spread. It's an abstract space of the system's possible states, and the butterfly is a shape drawn in that space of possibilities, not a shape in the sky. Physicists call it state space. And one honest footnote, measure that butterfly carefully and it has a genuinely weird property. Its dimension isn't a whole number. More than a sheet, less than a solid, a fractal. I'll leave that as a strange true fact and not compute it.
And strange attractor, that's a real term. Somebody coined it.
A real term, coined by two mathematicians, David Ruel and Floris Takens, in 1971, in a paper about, and this is our very next stop, turbulence in fluids. The perfect bridge, because everything so far, the pendulum, the map, the butterfly, has been a warm-up. Now I want to let this idea loose in something you see every single day, that the smartest people alive still cannot solve.
And before we go there, Lorenz himself, did he get the recognition? This is the founding idea of an entire field.
He did, and I want to be accurate because people love to reach for the obvious prize. Lorenz did not win a Nobel. There isn't really a Nobel category this fits, and he didn't get one, so if anyone tells you he did, that's wrong. What he received were two of the other great honors in science: the Crafoord Prize in 1983, which exists partly to cover the fields the Nobel leaves out, and the Kyoto Prize in 1991. A quiet man who found something enormous by retyping a number, properly honored for it, just not with the medal everyone assumes. The great unsolved problem. So here's where we walk right up to the edge. Turn on your kitchen tap gently and the water comes out glassy, smooth, silent. That's called laminar flow, and it's tame. Physics has it completely in hand. Now open the tap all the way. The stream goes white, churning, roaring, full of swirls inside swirls that appear and vanish faster than your eye can follow. That is turbulence, and turbulence is, with no exaggeration, the greatest unsolved problem in all of classical physics.
Hang on, that can't be right. Classical physics is the old, finished stuff. We've had the equations for fluids for a couple of centuries. How is water coming out of a tap an unsolved problem in the age of gravitational waves and quantum computers?
Because having the equation is not the same as being able to solve it, and that gap is the entire story. We do have the equation. It's called Navier-Stokes, and honestly you already know what it is. It's just Newton's second law. Force equals mass times acceleration, written for a tiny blob of fluid, plus 2 bits of bookkeeping, the push of pressure and the internal stickiness we call viscosity. That's it. Newton applied to a fluid. It's smooth, it's deterministic, and we've had it since the 1800s.
So we have a deterministic equation for the fluid, and yet
out of that smooth, innocent-looking equation pours all of this. Let me give you the one honest picture we have of what's happening inside turbulence. It comes from a great Russian mathematician, Andrei Kolmogorov, in 1941. Picture the churning water as a waterfall, not of water, but of whirlpools. You pour energy in at the big scale, the wide swirl of the whole stream. That big eddy is unstable, so it breaks into smaller eddies. Those break into smaller ones, those into smaller still. A cascade of whirlpools shedding whirlpools, energy pouring down from the large swirls to the tiny ones, until at the smallest scale, the fluid's own stickiness finally smears the motion out into heat. Eddies within eddies within eddies, all the way down.
that's a gorgeous picture, and I'm immediately suspicious of how gorgeous it is, because you've trained me to be. Is the waterfall of whirlpools the real thing, or is it a tidy story?
You've learned the lesson well, so let me be honest about how far the picture goes. Kolmogorov did wring one hard quantitative result out of it. He showed that across the middle range of that cascade, the energy carried by swirls of a given size follows a precise mathematical law, one famous enough to have a nickname, the 5/3 law. Most of the energy sits in the big swirls and cascades down to less and less in the smaller ones, following a 5/3 power when you sort it by scale. And that law shows up, confirmed in real measurements. in the atmosphere, in wind tunnels, in the ocean. So it's genuinely real. But, and here's the label, it is a statistical law. It describes the average, the typical energy at each scale, in an idealized turbulence imagined to be perfectly uniform and evenly stirred. Real turbulence is patchier and gustier than that. The clean cascade describes the average behavior, not a solution that tells you where any single swirl will actually go. Kolmogorov handed us the one piece of hard order inside the mess. He did not hand us the mess itself.
So even our best result about turbulence is a statement about averages, not an actual solution of the equation.
Exactly. And that brings us to the open wound. You'd think, we have the equation, we have supercomputers, so surely we can at least prove it behaves itself. And here's the shocking truth. For the full three-dimensional case, we cannot even prove that the equation always has sensible solutions. Nobody on Earth knows whether, if you start Navier-Stokes off with perfectly smooth, gentle conditions, it will stay smooth forever, or whether it can, all on its own, wind itself up into an infinitely sharp spike. A spot where the speed or the pressure runs off to infinity in a finite amount of time. A singularity out of nowhere. We do not know if that can happen, and we cannot prove it can't.
Wait, we don't even know if the equation stays well behaved. That feels like not being sure whether 2 + 2 might sometimes come out to 5.
It is genuinely that fundamental, and that's why it isn't only a physics problem. It's one of the most famous open problems in all of mathematics. In the year 2000, an organization called the Clay Mathematics Institute picked 7 problems they judged the deepest unsolved questions in mathematics, the Millennium Prize problems, and put a prize of $1 million on each one. Navier-Stokes' existence and smoothness, does a smooth solution always exist, or can it blow up, is one of those 7. And I want to be very precise about the status because this is exactly the kind of thing that gets oversold. As of right now, it is unsolved. Open. The prize is unclaimed. Every so often, a paper appears claiming to have cracked it, and I gently tell you, treat every one of those with suspicion, because none has been accepted by the mathematics community. Of the 7 original problems, exactly 1 has been solved so far. A different one, the Poincaré conjecture, settled by Grigori Perelman. Navier-Stokes is still standing, wide open.
So let me get the honest shape of this. We have the equation. We can simulate it and get pictures that look like real turbulence. We have Kolmogorov's law for the averages, but we cannot solve it in any closed form, and we cannot even prove it never explodes. Turbulence is genuinely not understood.
That is the honest shape, and you stated it more cleanly than most textbooks manage. We can compute with it, we cannot solve it, and the most basic question you could ask, does it always stay smooth, is $1 million mystery. Turbulence has been called the most important unsolved problem of classical physics, and whoever exactly first said it, it's true. And it's right there in your tap. The 2-week wall.
Okay, this is where I get to cash in the very first thing you told me, Lorenz and the weather. If the atmosphere is one giant, turbulent, chaotic fluid, then all of this, the exponential error growth, the butterfly, has to land on the weather forecast. Is there an actual limit to how far ahead we could ever forecast?
There is, and it's one of the most beautiful and humbling results in the whole business, and it is not the limit you'd guess. You might think the reason the 10-day forecast gets shaky is that our computers are too small, or our satellites too few. Getting better at those does help, up to a point. But underneath it all, there's a hard wall that no amount of technology can ever push through, and it comes straight out of chaos. Lorenz himself estimated it back in the 1960s. The atmosphere has a built-in horizon of predictability of about 2 weeks.
2 weeks? And that's not 2 weeks with today's technology. You're telling me 2 weeks, full stop.
Full stop. And that distinction is everything, so let me be careful about how solid it is. The 2-week figure isn't just Lorenz's old back-of-the-envelope guess anymore. In 2019, a team LED by Fuqing Zhang at Penn State, with Kerry Emanuel at MIT and others, tested it about as cleanly as it can be tested. Suppose we had a nearly perfect snapshot of the atmosphere and a nearly perfect model. How far out could we forecast even then? The answer came back at right around 2 weeks. 14 days-ish. They estimated that even with heroic future improvements, you might buy another 4 or 5 days at the very most, and then the butterfly wins. That wall is a property of the atmosphere, not of our machines. Chaos sets the limit, and we can only crawl up toward it.
So there's a fundamental ceiling, and the whole game is just getting closer to it. Which, okay, I have to ask about the thing everyone's talking about. Artificial intelligence. I keep seeing headlines that machine learning has blown right past the old weather models. Has AI beaten chaos?
Great question, and here I really want to hold the line between the exciting truth and the overblown headline. The exciting truth first. In the last couple of years, a group at Google DeepMind built machine learning weather models. One called GraphCast, reported in the journal Science in 2023, and a more advanced one called GenCast in the journal Nature, published at the end of 2024. And these things are remarkable. GraphCast produces a 10-day global forecast, and it beat the reigning champion, the physics-based model run by the European Forecasting Centre, on the large majority of the things they tested. Around 9 in 10 of roughly 1,380 forecast targets. And it does it in minutes, on a single machine, where the old model grinds for hours on a supercomputer.
9 in 10 of the targets? Okay, I want to make sure I'm reading that number right.
Hold on tight to that instinct, because GenCast is where the number gets slippery. It's an ensemble model. It doesn't make one forecast, it makes a whole spread of them to capture the odds. And the headline figure is that it beat the European Centre's own ensemble on about 97% of the targets they compared, more than 1,300 of them, and on nearly all of them, around 99.8% at the longer lead times. Now, that number, 97%, is the one I see mangled constantly, and I want you to get it exactly right.
Let me try and you correct me. It does not mean GenCast is 97% more accurate. That would be a claim about how much better each forecast is.
Correct. And that reading is just plain wrong. Say it the right way.
It means that out of all the targets they tested, all those different measures, at all those different lead times, GenCast came out ahead of the old model on 97% of them. It's counting how often it wins, not by how much. It wins almost every matchup. It is not 97% better.
That is exactly right, and the difference is not pedantry. It's the difference between an honest claim and a hyped one. GenCast wins the great majority of its matchups against the best physics model we have, and it's faster by an enormous margin, a real verified achievement. But now the 3 things it does not mean, because this is precisely where the headlines drive off the cliff. It does not mean the machine solved the Navier-Stokes equations. It never touched them. It learned patterns from decades of historical weather records. It does not mean anyone solved turbulence. Nobody did. And it absolutely does not mean we broke through the 2-week wall. We didn't, and we can't. These models are learning to sprint right up to the chaos horizon, more cheaply and more skillfully than ever before. They are not moving the horizon.
So, machine learning is a much better tool for getting close to the wall, but the wall is exactly where it always was.
That's the honest sentence. And here's a picture I'd leave you with, labeled as a picture. Chaos wraps the far future in a kind of fog. These models are a much better, much cheaper telescope for peering into it. Sharper, faster, and in the ensemble version, better at telling you the odds of what's in there. But a better telescope does not burn off the fog. The fog is made by chaos itself, and it is permanent. Better instrument, same wall.
I like that. It lets me be genuinely thrilled about the AI without lying to myself about what it did. So let me say the whole honest horizon back to you, the way you've been modelling all night. Deterministic chaos is real and proved. Sensitive dependence, the butterfly, the double pendulum, all rock solid. Feigenbaum's number and its universality are proved. A true theorem, the same fingerprint across totally different systems. The 2-week weather wall is a confirmed fundamental limit, not a technology problem. But turbulence itself is not solved. We have Kolmogorov's law for the averages and a lot of simulation, and no closed theory. And whether Navier-Stokes even always stays smooth is flat out unknown. An open million-dollar problem, with every "I solved it" so far unaccepted.
I could not have laid it out better. And holding those apart, this is proved, this is merely modelled, this is genuinely unknown, is the entire discipline of doing this honestly. And here's what I want you to carry out the door. That last one, the Navier-Stokes problem, isn't some exotic creature in a far corner of pure mathematics. It's the smoothness of the water in your sink. It's why the weather dies at 2 weeks. It's sitting inside the most ordinary thing in the world, and the smartest people who ever lived have not cracked it. The pendulum you solved for homework is one hinge away from it. The population formula on your calculator is one knob turn away. The frontier here isn't far off in some exotic realm. It's in the tap, in the sky, in a butterfly, hiding in plain sight inside laws you already know. And it is still wide open.
One hinge away, and still nobody's crossed it. That might be the most exciting thing you could have told me. Somebody listening could be the one who does.
Somebody listening could be the one who does. Go turn on a tap and watch the water break apart. You'll be staring straight at the biggest unsolved problem in classical physics, running for free in your kitchen. And then go do your next problem set, knowing the edge of the known is a lot closer to your homework than anyone told you.
One honest step past the homework. Until next time, keep your eye on the small things. Turns out a few digits past the decimal point is where the whole future hides.